Hello, good evening, and we're really burning the midnight oil tonight, but this is going to be the fifth and final portion of Lecture 15 of CENG 4412 Steel and Concrete Design, and this will also be the last lecture, or the last video covering covering material over reinforced concrete beams. Over reinforced. So this is the last topic I want to talk about for RC concrete beams, and really the last video entirely for this course dealing with beams of really any type until we get to say connections, or unless you were to classify slabs as beams or something like that. But and I know my slide numbers here are a bit off, but that's okay. This is a long lecture today. As you can probably tell by my voice, getting a little bit hoarse here. So anyway, and the topic here for today is going to be, for this video, is going to be hopefully relatively short. And this is going to be the idea of doubly reinforced members. So we talked about this briefly earlier, and I kind of misled you a bit when I said this can be helpful for strength design. As we'll see, doubly reinforced members often don't actually help that much for strength. But anyway, but they do have certain benefits to them. Doubly reinforced members, let's talk about these. Doubly reinforced members. So first of all, what does a doubly reinforced member look like? So let's for example consider a case like this. Let's say we had a beam that had two sets of reinforcement in it, both compression and tension reinforcement. Here. And something like this. Maybe more like this. And let's say the depth down to the tension reinforcement, was 56 inches. And let's say the overall depth of the beam, the actual height of the beam, was, let's say, well, I have actually here, that's a little bit of a typo. Let's say not 56 inches, but say 56 centimeters. And kind of an unusual unit for this class. Let's say the width is 30 centimeters. And the overall actual physical depth of the beam is maybe 60 centimeters. Here. And here, then my strain diagram would look something like, and then also let me show a few pieces of rebar here, compression reinforcement. So here, my strain, if I were to draw the strain diagram, it would look something like this. Here. Oh, don't want that. I would have linear stress strain through, not linear stress strain, but linear strain relationship throughout. And we'd have 0.003 up here, as we always do. And then at the bottom, we'd have, at the depth D of our beam, we have the strain in the steel here. And then we'd have some other ES prime corresponding to the strain in the compression steel. So looking at this here, let's say we were to assume that there's a perfect bond. So adequate development length, etc. Assume perfect bond. Perfect bond. Wow, that's really bad. Assume perfect bond. So basically epsilon S prime is equal to the epsilon of the concrete. But here, ES prime equals 29,000 KSI. 29,000 KSI, and which of course is much greater than 4,500 KSI for concrete that we might have for concrete. So in other words, so we of course know that in turn that the stress, the lowercase f, the stress in the steel is going to be much greater than the stress in the concrete. And so we would have then, in terms of overall forces, we would have some stress distribution up here. We'd have a large tension force down here. And then maybe distributed force or Whitney stress block up here. And then two equivalent forces. We could have our CS, the compression in the steel, and then CC, the compression in the concrete. But here's the interesting thing. If we're assuming that things are going to behave the same way, in other words, that plane sections are remaining plane, and that this steel here is firmly bonded with the concrete around it, this upper steel is not going to be able to go all the way up to the yield strength, nowhere near it. The upper steel, basically, the compressive steel, the upper compressive steel will not be fully mobilized. Cannot be fully mobilized. Because, or in other words, it will never reach the yield strength. Because it has to have the same strain as the concrete around it, the compression zone of the concrete. Because it has to have the same strain as the concrete. The same strain as the concrete in the compression zone. As concrete in the compression zone. In compression zone. And because it has the same strain, there, and because, so again, so we can kind of think of this here. If I do this little math, I could say E of steel compression has to equal E of the sorry, not E, S, has to equal strain, so epsilon of the steel in compression has to equal the strain of the concrete, at least at that given depth. And then I know, of course, that, well, I know that strain is going to be equal to F over E. So therefore, F in the steel divided by E of steel must be equal to epsilon, or sorry, F of concrete, the stress in the concrete, divided by the E of the concrete. And so basically, in order for this to hold true, I need that if these are going to be equal, basically the stress in the stress in the steel will be nowhere near its yield stress. Will be nowhere near yield. We're never going to be able to use that steel anywhere near its full capacity. We'll be nowhere near yield. So then the question is, if we're not, so it seems at first glance that making a double reinforced beam would be incredibly wasteful. So if we put a bunch of steel up in the compression zone, the compression region, embedded within the Whitney stress block, because it has to have the same deformation as the concrete around it, it's never going to be able to fully mobilize. It's never going to crack effectively. So the only way that's going to happen is if the concrete itself is crumbling, and at which point you don't really have a beam anymore. So the question then is, why build a double reinforced beam at all? Why would anyone ever do that? Well, a few reasons, and we'll discuss those. A double reinforced beam. Why build a doubly reinforced beam? And it is actually not due to strength. It's not for strength. Not for strength. Either way, T is going to equal to C. The equivalent point force, T is always going to be equal to C. And basically what tends to happen is, instead of adding more compressive strength, we don't need to add additional steel for additional compressive strength. If we need more compressive strength, and the tension steel can take it, if we need more compressive strength, the Whitney stress block just extends deeper into the section. If we need additional compressive strength, compression strength, the Whitney stress block just becomes deeper. The Whitney stress block just becomes deeper. Stress block just becomes deeper. Becomes deeper. Just becomes deeper. Okay. So here, now let's consider this here. And I'll show you that the actual MN width over MM without doesn't really change that much. So let me create a little, I'm going to create a kind of rough plot. And I'm going to have two things. I'll actually make this a little bit larger. So on this axis, I'm going to plot the rho prime over rho, where rho prime would be the compression reinforcing ratio, and rho would be the reinforcing ratio. So rho prime is the compression reinforcing ratio, and rho is just the reinforcing ratio in general. The reinforcing ratio. And let me show you Mn on this axis, the nominal moment capacity with and without the compression reinforcement. This would be Mn with divided by Mn without. So if I could design it once with and then the other without. And here, and let me label this on this diagram here. I'd also call this one, I'm going to call this depth here, the depth to the bottom reinforcement D prime. Or sorry, to the compression reinforcement D prime. So at default, I'm going to have maybe a 1.0 here. Then I'll have maybe a 1.1. And then maybe a 1.2. So the actual, so let me show some curves on here. First of all, our baseline is going to be 1.0. Just a baseline 1.0. No, I'm not going to really, and then I'm going to plot a series of curves showing various rho values. For example, for a rho value of 0.015 and a D prime, I'm basically just going to show a couple different combinations of rho and depth. So we get a curve like this, kind of here. If we had rho equal to 0.015 and D prime over D equal to 0.2 approximately, then if we had rho equal, again, everything just kind of levels out relatively quickly, rho equal to 0.015 and a D prime over D equal to 0.10. So you'll get different values depending on your D prime to D ratio. And we can get slightly, so for a really high ratio, you can get slightly more strength, a little over 1.0, sorry, a little over 1.1, so maybe 10% extra. And this is if you have rho equal to 0.75 here, and D prime over D. Actually, that should probably be rho prime over rho. Not you can't really have a rho of 0.75. That'd be a bit ridiculous. So rho prime over rho, rho prime over rho, I believe, if I remember my graph correctly. And well, actually, no, I have this in terms of just rho, so maybe that could be okay. I know that's a little bit odd, but that'll have to stand for now. So rho prime. So this would be where rho equals 0.75, and then D prime over D is equal to 0.10. But don't worry too much about this. The real thing that you need to keep in mind is that we can, so don't worry too much about the specifics of that graph. I know it can be a bit confusing. The real benefit of double reinforcement is not strength. Is not strength. The strength benefits are modest, you know, less than 10% usually, at least for positive bending. The strength benefits are modest, are very modest. Usually less than 10%, as what that previous graph was trying to show. I think I need to rework that. There's something wrong with the labels. Less than 10%. So though, Now, we do have some real benefits though. So let's talk about what the real benefits actually are. And maybe I'll do this in the next slide. So the real benefits are not strength, but other things. The first really comes back from the previous lesson, previous video, part 4 of this lecture. And this is one that you get reduced long-term deflections. Reduced long-term deflections. If you remember previously, we saw that was one of the important factors. So, in other words, here, if I were to create a plot here of time, I don't like that or that, of here, maybe time. Maybe this is 120 days. Maybe this is 240 days. Maybe this is 2 years. 2 years. And maybe we have a delta. So you might have a beam like this. A delta in inches. Maybe you have something like, 2 inches, 4 inches, and 6 inches. And maybe kind of extend this along for, let me just provide some plot lines on here. And like this. And so if rho prime, so maybe your initial, let's say for each of these, the lines I'm going to draw, maybe initially the initial deflection is 2 inches. Well, if you're going to have if you have no compression reinforcing, you might get something more like, well, that's not quite what I want. Maybe you're going to get something more like this, where it's going to, over time, increase quite a bit. And so this would be perhaps where rho prime equals 0. You have no compression reinforcing. Then maybe this would be a middling zone here. Kind of like this. And then if you have a very high ratio of compression reinforcing, you might get something like this, where you would still get some, it would still increase a little bit, but this might be where rho prime is equal to rho. The ratio of, where the ratio of compression reinforcement is the same as the ratio of tension reinforcement. In other words, you have the same amount of compression as tension reinforcement. So the compression reinforcement is going to do a lot to prevent creep. So again, creep of concrete results in long-term deflections, in larger long-term deflections. Results in larger long-term deflections. Long-term deflections. Long-term deflections. And again, because concrete is an amazingly lazy material. But the moment we lock that concrete down with some compression reinforcement and say, no, you're not going anywhere, then suddenly the amount of creep will greatly decrease. So doubly reinforced beams have less initial compression. I should actually say you get less creep because they have less initial compression stress, less initial compressive stress, and therefore will have less creep in the concrete. So less compressive stress in the concrete, so therefore less creep and less long-term deformation. Another benefit, concrete is not known for its ductility and steel is. So increased ductility. And ductility, of course, correlates with the ability to absorb energy. So ductility means the ability to absorb energy. And so if you increase the steel content, especially both tension and compression, you increase your ductility. You increase the amount of energy that can be absorbed. And this is actually very useful for one particular thing, and that is seismic design. So if you have if you're designing reinforced concrete buildings in a seismic zone out in California, you're going to see lots and lots of doubly reinforced members. Even if it's not strictly necessary for strength, the extra ductility is a great use and often required by code. And also, what else? This also changes the failure mode to T, to tension. It will change the failure mode to a tension failure. Basically, we're deliberately sort of over providing compressive capacity to tension. And this can be good because a ductile failure is better than a brittle failure. 4, this can make fabrication easier, especially if you already need shear stirrups. Basically, you can hang the shear stirrups from the compression reinforcing. So this decreases your labor costs, etc. Because you can hang stirrups from your compression reinforcing. From compression reinforcing or reinforcement. So for example, if you have a concrete beam like this, something like this here, 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 and here, your stirrups can actually just be hung and wrapped around kind of like this. Like so. And finally, well, we haven't talked a lot about negative bending, but everything what we've usually when we talk about tension reinforcing being at the bottom, the assumption that we're actually, I guess always when we say tension reinforcing being at the bottom, we're making an assumption. And that assumption is that we're under positive bending. But however, if you have a beam that may be under positive and or negative bending, depending on the loading, having some compression reinforcing can be very good and it can be absolutely necessary because if that beam is ever going to go into negative bending, well, all of a sudden the compression zone will be on the bottom and the tension zone will be at the top. And if you don't have any steel at the top of your beam, you're going to have a bad day. So this is very important if you ever have beams under negative bending. Negative bending and this is very useful, or especially for continuous spans, so if you have any kind of continuous span or continuous beams, maybe I should say continuous beams instead of continuous spans. In other words, beams that continue through more than one span. So for example, especially for continuous beams, it is basically unavoidable that a continuous beam will have one or more of its spans in negative bending. So for example, if you have say a beam like this, if you have a series of spans, or maybe something like this here, if I go and apply a load of maybe a point load, let's keep it simple, just a single point load at the center, what is the deflected shape going to look like? Well, the deflected shape, right at the point of application, that makes sense. That's going to go into positive bending. But at the pins here, or the rollers, we'll have a inflection point, and now the other two spans will be in negative bending, like so. So we'll have negative bending, positive bending, and negative bending. So this is very important for any kind of continuous spans. You see this a lot on, say, pre-stressed highway bridges, pre-stressed any kind of long span structure that has beams spanning across multiple supports. But so yes, here, basically here, your compression steel, well, what we normally call the compression steel, this would be in tension. So this would be in compression here, and this would be in tension. And so, and this is now you might think, oh, I'll just flip my beam. You might just think, oh, if I want to design that, no problem. I don't need steel on the top and the bottom. I'll just have steel only at the top, but not at the bottom. Well, this load, or this tends to happen is things like bridges, and that big heavy point load is probably like something like a big truck, and that truck may be driving from the is not going to just it's not going to teleport into existence in the middle span and then just sit there for all eternity. No, it's going to go from one end of the bridge to the other end of the bridge, and each span will enter periods of positive and negative bending, positive and negative, positive, negative, positive and negative, as that large point load or truck moves along the length of the span, or length of the bridge, or the length of the beam. Okay, and so in turn, for any kind of setting where you have continuous beams, you will need to then in turn design them to handle both the maximum possible positive moment and the maximum possible negative moment. And so there, what we call compression reinforcement or double reinforced beams are not only more efficient, but they're also absolutely necessary. All right, so that'll do it for this lecture. Finally, we're finished. This is going to be, so we're now finishing the last lecture for reinforced concrete beams, last lecture for beams entirely, and tomorrow's lesson 17, or sorry, I guess lesson 16, will be started with column design. All right, that'll do it for tonight. Thank you for watching, and as always, thank you.